Hello, welcome to this talk on GitOps, Kubernetes, and secret management with Jenkins X. I'm Cara Delamark. I work at Cloudbase with the Jenkins X and Jenkins open source projects. Jenkins X is a CI/CD platform on Kubernetes with GitOps built in and committed to facilitating GitOps best practices. In this talk, we'll focus on secret management within the context of GitOps and Kubernetes. And secret management is an issue across software development, but in this talk, we're looking at it with GitOps and Kubernetes. As an example case, we'll also discuss how Jenkins X manages Kubernetes secrets securely using external secrets. Okay. First, let's talk about GitOps. GitOps uses Git as the single source of truth for declarative infrastructure. The version control system used does not have to be Git, but Git is the most widely known and used version control system in the software industry today. With GitOps, the entire state of your system is described using declarative specification for each environment, and these are stored in Git. This means all infrastructure configuration, as well as application code, are stored in Git repositories. GitOps as a term indicates the ability for teams and developers to manage infrastructure with the same Git-based workflows they use to manage a code base. GitOps enables operations by pull request. In practice, this means instead of making changes directly to the system using a UI or CLI, changes are made to configuration files stored in Git, representing the desired state of your system. These proposed changes can then be reviewed by other team members, and once approved, merged to the main branch. That is, the exact same Git-based workflow developers are already familiar with. One key benefit of GitOps is that it enables the same rigor of code reviews used on the application code to be applied to changes to the application operational environment. The underlying idea here of infrastructure as code isn't unique to GitOps, but it is foundational for GitOps. GitOps is building on the existing DevOps practice of infrastructure as code. So, what do we mean by infrastructure as code? First, infrastructure config prepares files that prepare computing resources such as server, storage, and load balancers, which are needed for the software application to operate correctly. In practice, infrastructure as code means that infrastructure config changes are codified, and the source code for the infrastructure is stored in a version control system. This makes the deployment of infrastructure repeatable, more efficient, and more reliable by reducing human errors. One of the nice inherent advantages of infrastructure as code is that when you define infrastructure as code, the code documents the intended setup of your infrastructure. You've documented the desired state of your system in Git. DevOps essentially centralized on declarative infrastructure as code. Okay, so what do we mean by declarative? With declarative systems, you describe how you want the system to be, not all the steps required to get there. A declarative system enables idempotency. So, idempotence, what is that? It means that multiple applications of convergence have the same outcome, which means that convergent actions can be applied multiple times without changing the result beyond the initial stated desired outcome. And one way to think of this is, for example, like elevators. You get into the elevator and you press which floor you want to go to. You do not say, I need to go up 2 floors or down 2 floors. So you can get in an elevator and there's no big plus or minus buttons. You just press the floor, number 5. And you can press floor number 5 20 times and it will always take you to the 5th floor. So this is similar to that idea of repeated actions of convergence, always bringing you to the initial stated desired state or outcome. Okay, so this idea of idempotence is central to how the actual state of your system is kept consistent with the desired state of your system declared in Git. In fact, idempotency is incredibly important because the desired state and the actual states will be continually diverging. And what is aimed for is eventual consistency, as multiple actions of convergence may be applied to the actual system. So for GitOps, what are the necessary elements? And GitOps, as we've said, very much embraces and builds on this practice of declarative infrastructure as code. And building on that practice, in addition, you have orchestration and observability, which are necessary for GitOps. GitOps consists of these practices. all of which existed before in some form or other, and bringing them together. So we have DevOps, declarative infrastructure as code, orchestration, and observability. Okay, so GitOps doesn't require a particular set of tools, only that they enable the following: that they operate on the basis of the desired state of the system. That is what is stored in Git. And this is your declarative infrastructure as code. And as well, you will have your application code as per normal in Git as well. And it detects the differences between the desired state and the actual state. So this is the observability into your system. And it performs the required operations on the infrastructure to synchronize the actual state with the desired state. This is the orchestration, and it's what enables the convergence. And this idea of orchestration is game-changing. Orchestration comes about and is dependent on having a tool which uses convergence to control exactly what's running inside the system. This would have previously been done in an ad hoc and possibly human way, but with GitOps, this is now done systematically. And it is done systematically because it is done by automated software process. In a container-based world, this is done through Kubernetes or Docker Swarm and Mesosphere, etc. But in this talk, we will concentrate on Kubernetes. The concept of orchestration is one which is based on managing to a plan. That is, it is continually synchronizing between the intended state, plan, and the observed state. In this case, what the orchestrator can see is the observed state. And observability is essential for GitOps. An orchestrator, or sometimes called an operator, and often an automated software operator, needs to be able to determine an environment's running state. The operator can only make informed decisions on what changes to make once the system's current running state is known. However, the actual current state can never be actually known. All we can do is observe what the state is through observability tools, and that gives a way of seeing what might be true about our actual system. And this is as true for humans trying to observe the system as it is for the operator software process. So one of the benefits of GitOps has been this drive for greater observability into the state of your system. And proper control of an environment requires observability of that environment. Because of this greater drive for observability, there have been a number of benefits that have accrued for developers. For example, human observability into the system is often made easier and more convenient for developers by cloud providers, which provide a number of methods to promote observability, such as APIs and dashboards, etc. This makes it convenient for users to understand the current state of the environment. And it's important to note that these requirements of GitOps could also have all pretty much been listed as benefits of GitOps. So there are a lot of benefits that come out of GitOps. Additional benefits include auditability, because all of the changes are going through your version control system, and those changes are recorded, they're easily visible and auditable. And this enables problematic changes to be reverted. So a huge benefit of GitOps is that it enables traceability of changes made to an environment and enables easy rollback, recoverability, and self-healing using Git. So, another benefit of GitOps is that it empowers developers. We briefly mentioned this before, but GitOps enables developers to manage infrastructure with the same Git-based workflows they use to manage a code base. This advantage of GitOps, that it allows self-service of infrastructure change by developers, provides a good balance between control through code reviews and the ability to roll back changes, and improved development and deployment speed. For those already doing DevOps or infrastructure as code, GitOps can be really appealing because it applies the existing processes and it brings them closer to the developer. And developers can use the tools they already know to provision infrastructure and push code into production. Okay. This is a real shifting left. So we'll do a quick high-level overview of GitOps. And at this high level, your desired state of your system is declared in Git. And this is the single source of truth for your system. So with GitOps, there is a single source of truth for what is happening in the system from both a software development point of view and infrastructure perspective. The other part of GitOps is being able to observe the actual state of your system and reconcile that actual state with the desired state as described in Git. Now, Kubernetes helps a lot with this. It handles active reconciliation within your cluster. In addition, it facilitates the scaling of applications, containers, and the underlying necessary infrastructure. As we've said, GitOps can be implemented independently of Kubernetes, but using GitOps with Kubernetes is a natural fit, with the deployment of declarative Kubernetes manifest files being controlled by Git operations. And Kubernetes, open source by Google, is the most popular container orchestration platform. From the developer's point of view, GitOps with Kubernetes means that the same process they use to merge code using pull requests can be used to deploy Kubernetes. This is an example of what is called self-service infrastructure, which is empowering for developers. Kubernetes deployments have the following properties that we've already identified as important for GitOps. So automation. Kubernetes automates the process of applying changes correctly and in a timely manner. Convergence. Kubernetes will keep trying to update until the update is successful. And idempotence. So you have multiple applications of convergence, and they will have the same outcome, which is your stated desired outcome. The combination of GitOps methodology with Kubernetes declarative configuration and active reconciliation model combine to provide a number of operational benefits that result in a more predictable and reliable system. So when doing GitOps with Kubernetes, you need a GitOps Kubernetes operator, which automatically ensures that the state of the cluster matches the config in Git. The operator pulls the Git repo for changes or divergence between the desired state and the actual state and triggers deployments in Kubernetes. It makes sure your new cluster images and config changes are propagated to your cluster. So when following the GitOps model, the desired configuration of the system is stored in Git, and an operator software process, in our case, literally a Kubernetes operator, is responsible for changing the current state of the system into the desired state of the system. So at this overview level, we've seen that GitOps is centralized around using a version control system, such as Git, to house all information, documentation, and code for a Kubernetes deployment, and then uses automated operators to deploy changes to the cluster. You could see GitOps as an operating model for Kubernetes and other cloud-native technologies. What is important to recognize is how centralized it is. There's one single path for managing operations and development. This sounds relatively simple, right? But there are areas and concerns where GitOps becomes more complex and harder to implement correctly. Secret management is one of those areas. So the problem of secrets. Having all configuration files version controlled by Git has our advantages, as we've seen, but securely managing secrets in such a system has proven difficult. Basically, having infrastructure config and deployments declaratively described in files in Git raises issues of secret management. So, what are secrets? A secret is anything you want to tightly control access to. Kubernetes provides a mechanism allowing users to store bits of sensitive information in a protected resource object called a secret. So Kubernetes provides a built-in object for managing secrets called a secret. Common examples of data you would want to store in a secret include username and password, SSH keys, API keys. Okay. So here's a simple example of a Kubernetes secret. As you can see, it has 3 major pieces of information: the name of the secret, a type, which is optional, and a map, which is maps field names to sensitive data, and these are encoded in base64. The Kubernetes object is convenient to use, as it provides a declarative API that makes it easy for application pods to access data without any special code. And when you first see a Kubernetes secret, you may be tempted to think that the values are protected by encryption. But in fact, they are not. Base64 encoding allows binary data to be represented in ASCII strings format. It does not provide encryption. The reason Kubernetes does the base64 encoding is so that secrets can store binary data. This is important for things like storing certificates of secrets. Okay, so you do not want to store raw Kubernetes secrets in Git with the base64 encoding, which is like plain text. And here we can see the secret data, which has been easily unencoded, reading username, that's all join, and password, and eat cake. GitOps practitioners may be very happy to store their configuration files in Git, but they are unwilling to store their sensitive data in Git due to security concerns. In fact, our one rule for GitOps, Kubernetes, and secret management is don't store raw Kubernetes secrets in Git. But we're trying to do GitOps and have the entire state of our system in Git. So what do we do? Luckily, there are a number of potential solutions. They all come with trade-offs. But in this talk, what I'll be focusing on is how Jenkins X, as a CI/CD platform on Kubernetes, approaches secret management. So Jenkins X encourages the use of an external secret management system. These specialized systems can do a lot for you. They securely store and manage your secrets. They provide identity-based access to sensitive information, and often they do data encryption in flight and at rest. So there are a variety of external secret management systems that exist, and one of the most popular is HashiCorp Vault. In addition, the major cloud providers offer secret management services as well, such as Google Secret Manager, AWS Secret Manager, Azure's Key Vault, Alibaba's Cloud Secret Manager. And these might have different features, but the general principles are the same. So in this strategy of using an external secret manager, rather than using the native Kubernetes features to store and load secrets into the container, the application containers themselves then have to retrieve the secret values dynamically at runtime at the point of use. So when using an external secret store, it is the responsibility of the application to retrieve the secrets from the store securely. And often teams develop custom solutions for accessing secret data. The result is that there are overlapping efforts for developing solutions, and because security is vital in this context of secret management, each individual effort can require substantial engineering time. And so all that gray space in the slide, in that diagram, that is your engineering time. So luckily, there's Kubernetes external secrets, which has been open sourced by GoDaddy. And Jenkins X highly recommends using Kubernetes external secrets for secret management with GitOps and Kubernetes. So what Kubernetes external secrets does is it enables the secure retrieval of secrets stored in your external secret management systems and the ability to securely add secrets to your Kubernetes cluster. The project extends the Kubernetes API by adding an external secrets object using a custom resource definition and a controller to implement the behavior of the object itself. So an external secret declares how to fetch the secret data, while the controller is responsible for fetching that secret data from external providers and converts all external secrets to Kubernetes secrets. The conversion is completely transparent to the pods, who could then access the secrets normally. Kubernetes external secrets work well with external secret management systems such as HashiCorp Vault and the ones of all the major cloud providers. So Jenkins X highly recommends using Kubernetes external secrets for secret management with GitOps and Kubernetes. And Jenkins X, as a CI/CD platform on Kubernetes with GitOps built in, is committed to facilitating GitOps best practices for users. Jenkins X enables users to manage installs, upgrades, and rollbacks via Git. The GitOps workflow is the backbone of Jenkins X and provides users with the peace of mind for disaster recovery and proper secret management that is important in disaster recovery. For secret management, the Kubernetes external secrets means you can check in the external secret resources in Git, which are a reference to the actual secret values that are stored in some provider. Jenkins X supports the major external secret management providers. Jenkins X has chosen a secret management approach that adds an abstraction layer above secret management solutions, so users can choose where the source of their secrets can be stored, preferably outside of your Kubernetes cluster. And this is a good practice for disaster recovery as well. Thank you for listening to this talk on GitOps, Kubernetes, and secret management. There are some links in the slide with more information, and I'd be happy to answer any questions you have either now, if we have time, or you can contact me at the links. Thank you.